So before we start the session, the highlight would be on your front camera. I think the PC one.
That's right. So this may not be there because it
Yeah.
will confuse people with. So I could just momentarily stop video.
Yeah.
Oh, video. Okay. Yes. So I can do that whenever I.
Yeah. Whenever you want, like whenever you want to show your work area, you can switch on that video.
That sounds okay.
Yeah.
In case I miss, do give me a ping because I'll assume sometimes that the camera is on as well.
Yeah. I'll tell you whenever. Just give me a minute, sir. So to start with, I'll just give your introduction. I think the introduction is those points that we have already written in the message. So that's it. And I think about the material, have you made any slide or something like that where you're going to ask them like, are they ready with the material or something?
I have a slide. Yes.
Okay, fine. So we have 3 teachers who are in the waiting room. I'll just call the other 2.
Sure.
And then we'll start.
Then continue with the ice cubes couple. Can you hot pot please? Yeah, बचा please. 2 only. 2. चार बत्ते
Hello. Yeah. So we'll start. I think we have 4 teachers have come. The rest 2 teachers will join in later.
Okay.
Yeah. So I'll let in these teachers. Good evening, all the teachers. Is my voice audible?
Yes, ma'am.
Yes. Thank you so much. So a very good evening to all the participants in today's session. My name is Varsha, and I welcome you all to the session on rebuilding our relationship with water. I also welcome you all to this Navnirmiti Eduquality's platform, online platform. So before we start the session today, let me introduce you to our resource person. I would request teachers to mute themselves for say 5 minutes till we start the session. So yeah, as I was saying, let me introduce our resource person for today, Mr. Deepak Malani. He's trained in engineering and research from IIT Bombay. His imagination is that all of us should get sensitized to the fact that water is life. He explores water bodies through riverside walks, kayaking, and river and lake restorations. He has hosted hundreds of people to reconnect with rivers through many activities. So I think, sir, I welcome you to Navnirmiti Eduquality's webinar platform. I hope that all our participants are really very much excited. I know that we have, for today's session, we have fewer participants with us, but the excitement is something that due to which we have, still kept this session going on. So I really appreciate the efforts of the teachers who have come here today for the session. So I hope that you take the most of it from today's session. So over to you, Deepak, sir.
Yeah, thank you, Varsha, for a kind introduction and for setting up this session on Sunday. And thanks to all the teachers who are able to join us this late afternoon on a Sunday. I understand that in today's times, it's very challenging for teachers to continue the same way of teaching with children as it would happen in the classroom environment. The pandemic has brought us challenges, but also opportunities to be able to reach out to people far and apart. Right? So we'll hopefully have a good hour of conversations, not just one of us talking and others listening, but each one of us sharing some of our learnings, our insights and observation on this topic of water.
Hello, sir. I think there's some disturbance from your side.
Yeah, there is some kind of festival celebrations going.
Okay.
Neighbor.
Okay.
Okay. But is my voice loud and clear?
Yeah, teachers. Like I am able to hear properly. What about teachers? Hello?
Yeah, we can hear.
Okay. Thanks. Just that we get to introduce each ourselves a bit more. I would invite the participants. I see there are 4 teachers who have joined us. If you can tell about briefly a few lines about you being a teacher and your expectations from this session, if you have thought of something that will also set the tone for today's webinar. So if I could just nominate one person who can introduce themselves, tell us what subjects do you teach, what age group do you teach, and if you have any comments for today's session, let me begin with that note. So may I just nominate one of the teachers, Miss Mary, if you could tell us about yourselves. You will have to unmute and if possibly maybe just share, unlock your video also during the time of your introduction, and then you can switch off the video if you're comfortable that way. Ms. Jai, do you want to go first?
Hello, Jaya ma'am.
Yeah, yes. Good evening, sir and ma'am. I'm very happy to be here. I know we have a lot of expectations, though we are teaching in the school. Now what we are doing is completely different, and our experience is very different, and the teaching methods that we are using is also very different from what we were using before. So really, we like to know more and more how to get the children online. It is not only the teaching, but also how to get to give them the values that they have to inculcate in their lives. Maybe it is science or whatever subject it is. It is not only moral science, but science also can teach them values. So these things we need to really inculcate in children. And then I don't know whether we can give them first-hand experience in online classes, but still something we can do for them, which they will learn for the lifetime. And I'm a teacher working in Carmel Convent Higher Primary School, and I'm teaching for class 5 and 7 science. So I'm looking forward to something nice in this session. Thank you, sir.
Thanks, Ms. Jaya. Ms. Rukmini, do you want to tell us about yourself?
Good evening, sir. Good evening, teachers. I'm Mrs. Rukmini Ambati. I have been teaching in school for past 15 years, and science is my core subject. And this year we have opted for a new subject introduced by our department, water security. And the moment I saw this, actually somebody has passed on this invitation to me, and I said, okay, let me give it a thought and see what it could be and how it would help my subject. So basically, I'm sitting here with many more expectations, and I want to take this experience to my students in my classroom, though it is online, but we will surely try to do what you will be showing us today, sir. Thank you.
Which age group do you reach out to? What classes?
I teach 8th, 9th, 10th standard.
And that subjects of science as well?
Yeah, science.
Thanks. Ms. Sugandhi, if you can unmute yourself, that'll be great. Yeah.
Yes, sir. Good evening, sir.
Very good evening.
Good evening, teachers. I am Sugandhi, working in Carmel Convent, handling science for 5th, 6th, and 7th. And by seeing this link, I would like to see how we can show them the experimental or what is available at home and near that, because science, they need experiments to be shown, but it is we are doing it in online. From home, we are taking the classes from home. So what is available, how to show them the experiment, what is available at home. So I am looking forward that you may help us to do that. We have asked the children to join. 1 or 2 girls, they were joined, and they told they are not able to join now at the last minute. They were very interested. Now they are not able to join. So I'm expecting that how we will be able to demonstrate at home through online to see that water, especially they have learned about the water, what is that, where it is available, and more than any other extra thing we can say to them that we need. Thank you, sir.
Sure. Right. So, Ms. Sugandhi, if the students are still online, and if you can share with them the Zoom link, and Varsha, if you think that's technically possible to accept a couple of more participants, we could readily take them in. So they're students, good to see their reaction in some of the activities that we do.
Definitely. Yeah, ma'am.
We can share. I want to ask this one earlier, whether we can share the link, because suppose we can, somebody is conducting that, passing the link, we are not supposed to share the link. No?
Yeah.
That's why I didn't ask. I was supposed to ask.
Yeah, ma'am. I think 2 of your students had contacted. But they didn't want, like, they didn't want to attend today. Even if they're interested, you can share the link with them.
They told that they were able to. They told they were. They were so disappointed, ma'am. I was rejected, and then and after they get that message, and then immediately they were.
Okay, so you can share the link with them, ma'am.
I don't know whether they told they have to go somewhere. They've gone.
Yeah, exactly. Yeah, we tried contacting them.
So we may be able to do another session some Sunday later, and we can reconnect with those who could not attend it for multiple reasons, either technical or festival or other examination duties, as I'm told. Thanks, Ms. Sugandhi. Miss Mary, are you able to unmute yourself and share a bit about yourself? Or maybe you want to put a message in the chat box in case your audio setup doesn't support you at the moment. I hope our audio and video is going to all the participants. Okay, so good time to begin now. And as you felt, the current times through which the teachers and the students in a school environment have interacted all these years, in the current times we have certain challenges. So this is one of the themes that we'll address in today's session, and I hope we can make it interactive. So I have a few activities that I'll be putting across and related to water. And I hope we are able to rebuild our relationship with water, as the theme of this session is, in more than one ways, and we'll be able to connect the dots between these different demonstrations and some of the slides that I may have to share. There was a small list of materials that I had shared with you all. In case you were able to manage them, it's fine. In other case, I would share all what we have done today. We'll have a recording of today's session, so you can revisit them even if you don't have all the materials around with you. So and thanks very much for expressing your expectations, and I hope we can address them. Feel free to interrupt me in between. You can unmute yourself if there's something that you either are not able to hear clearly or see clearly, or have a doubt about the activities, or even have some ideas to add in. So it's not just one-way flow that I hope will be there today, but since many of you have years of teaching experience, and you know, you have interacted with students across different age groups. So if there are some lessons that you want to share with all the participants, that would be even great. So let's treat this as a round table session, and that'll be very nice. So there should be some takeaway for me as well through all of your participation in this program. So let's we'll intersperse a few demonstration activities and also some conversations about how did I end up exploring water as a theme. Right? So I have two devices, one on which I'll be sharing my screen, and another is this phone device that will allow me to show you what I'm doing on the table. And participants may join in or may have some technical difficulties in between while we hopefully continue the flow. Welcome all teachers who have joined today. You can try to replicate in case you have been able to arrange the materials. Is it possible, if you're comfortable, or those of you who are, if you can switch on your video, if you're very comfortable with that, and that would then mean that at least I'm able to see some of you at least, just like you would expect your students also to switch on their cameras, and that would mean that this is a real live session that's going on. Can I request the teachers to at least switch on for at least the first few minutes of the interaction? Yeah, you can think that we have to take a group photo of all the participants and send a report to our head office. So other than the names, if there are faces on this Zoom screen, we can take a snapshot. Varsha, I hope the bandwidth would be good to be able to share all of this. Thanks. Thank you. Thanks. Yeah, thanks. Okay. So some of these experiments would be something that you would have already tried out, but let's just begin on the properties of water. Now, some of these experiments may be, hi Suhani, are you joining by yourself, or you also have a hi?
And now I'm joining by myself.
Oh, that's great. Okay. So, so our desire to have both teachers and students is now well achieved. Yeah, thanks for joining in at this moment. So, so Suhani, feel free to interrupt me if I'm going a little too fast, or if you're not able to get what I'm going to talk or show about. Feel free to interrupt, share your curiosity with us. So we'll have a set of experiments that we will talk about. And since these may be ranging across different age groups based on the prior exposure of these students, like class 5 students may have just got started with the basics of science, materials, water, liquid, solid, different phases of materials. So we should be able to have different depth for every single experiment that can cater to students right from class 5 to class 10. And sometimes even scientists are not too sure of certain properties of materials like water at times. So let's keep that as a basic disclaimer that all of us have little understanding of this as simple a topic like water, while there are continuous explorations that are happening around this. Okay, so I would want to begin first with an experiment where you take a glass of water, and then if you have ice cubes in your refrigerator, you can go pick those and put it in the glass and then add water into it. So, Suhani, if you feel this is also comfortable to you, if you can, if any of these experiments you need to take assistance of an adult at your home, please feel free to have them around you. It may be good to have them as well.
Thank you, sir.
Okay, so I hope you can see all of this. I have oriented my camera top down, and I have this empty glass of water, a transparent glass, and then I'm putting a couple of fresh cubes right, in this. Okay. Fresh ice cubes from the refrigerator, and you can hear the clinking sounds, okay, in there. And what you would see, so may I just ask, Suhani, are you still around? Oh, she has, maybe she's disconnected. Okay. No worries. Oh, so what happens when we put in water in this glass? Where do the ice cubes really remain? And for how long do they remain? So yeah, Suhani, we did a small experiment. Suhani, feel free to keep your video camera on, right, so that I know that you are either on the desk or you are going around with looking out for the materials. So as you would see that the ice cubes are floating. They are not at the bottom, as one would really think that an object like a coin, a solid coin, would just sink at the bottom of the glass. That's not the case with solid water. So what is ice? Ice is essentially solid water. And you see that the ice cubes are pretty much floating at the top. Right? Now, these may be very familiar, seeing that, yeah, indeed, ice cubes really float on the water, on top of the water. Just a point. So while if I take a 5 rupee coin and put it in the glass, you know it has gone immediately at the bottom. So a metal coin sinks at the bottom of a filled glass, while the ice cubes, they have shrunk in size. But if I put another one, you will see that it's floating right at the top. Right? I know that the camera angle is not very friendly for seeing this flotation, but maybe if I shake this around, you see it for yourself, and then of course students can also see it. So any one of you want to take give an explanation of this? Why does the metal coin sink while the ice cubes, both of which are solid, they show a different behavior in water? It'll just help us. We know it all, but it'll just help us get the conversation going.
Because of the density.
Okay, if you can complete that explanation, that'll be nice.
Yeah, the metal coin is more denser than water, whereas the ice cubes are less denser than water.
Fantastic. Yeah. Does anyone want to add something more to that explanation? That's a very reasonable explanation, but is there something more to it? And we typically know that solids in a particular form. So you take iron, for example, the liquid iron versus solid iron. As the material solidifies, it's denser than its liquid version. So why isn't solid water denser than the liquid water? That's a follow-up question. Right? If we could
The
elaborate on that.
molecules are arranged close together in solids, and it will be very rigid, hard solids. And the liquids there, the molecules are not so arranged close together. They have intermolecular space, and the forces are very less compared to that.
Indeed, right? So in metal, the individual atoms of the metal, in metal case, or whatever is the base, smallest dimension of that particular, it could be a molecule, it could be atom, or it could be a complex molecule of any given solid, is densely packed compared to when the same material is in the liquid form. And once we even heat it further, if it becomes gaseous, the molecules are separated even far apart. So the density reduces as the material changes its state from solid to liquid to gas. But in case of water, we would expect that the solid ice should be denser than the liquid ice. Why don't we see that? And what are the repercussions of this kind of behavior of water? Yeah, it's okay to express our current understanding. It's a round table, and then we can help each other get a little better understanding to our extent. So, Ani, did you see that the ice cubes were floating?
Yes, sir.
Yeah, okay. Have you seen that kind of phenomena anywhere else where you've seen ice in any form floating on top of water?
No, sir, but I have seen the ice sinking in, like, when they try with the dry ice into the water with a bucket, they hold it up. So
Okay. Yeah, so you say, I mean, dry ice technically could mean something else, but you mean when you put ice cubes in a glass of water, the ice raises up, right? Is that what you meant, Suhani?
yes, sir.
Okay, right. So we see that this behavior is not behavior of water in its two forms, solid and liquid, is not similar to what we would expect out of, say, any metal, right? And that is referred to as the anomalous behavior of water. There's something different that's happening in case of water. So before we talk about the science behind it, but let's see what would have happened if water had the same behavior as you would expect with any other material. So what if ice was denser than liquid water? Can you think, this kind of a what if question, but can you imagine the life around if that was the case, if ice would sink down if it was formed somehow in a water body?
Then we wouldn't have Antarctic and Arctic regions.
Okay. So do you believe the ice caps in those regions are indeed floating on water?
Not throughout the year, but sometimes.
Okay. So you're saying that the polar caps would have not been the way they are if ice really submerged in water. Okay.
And in case of iceberg, half of them will be there inside, no?
Yeah.
Right.
So our typical idea of iceberg is something where the water level is somewhere in between. That's how icebergs are represented. Okay, so this is interesting. Yeah, and I'm yeah. Now we'll have to relook whether the polar ice caps, how much of ice they are in entirety versus how much of it is a formation on top of a land mass. Okay. So there's a equal chance that there is a land mass underneath the icy regions, the icy caps on which they are held. We'll have to really see. I do not claim to know that answer, that the ice caps are indeed all floating on water. So because the formation of the ice caps and the formations of mountains like Himalayas have a little common past. One would think that way. Now take this example of a frozen lake. I think in India, Dal Lake in North India, around in the state of Jammu and Kashmir, freezes in some part of the year, in the colder parts of the year. Now, because the ice is floating on top of the water, as the water starts to get cold and reach its freezing point, there is a thin layer of ice which then gradually thickens up to some extent. Now, because the ice floats on the water, that frozen icy layer is at the top of the lake. Now, what does this do? Does this process continue, that the whole lake gets frozen, or does it stop somewhere? Do you have any idea about this particular example of frozen lakes?
Sir, may I?
Yeah, please.
Once a thin sheet of ice is formed on the lake, the water below the ice remains at 4 degrees centigrade. It doesn't go below 4 degrees Celsius because ice behaves like an insulator. It does not allow that heat exchange between the surrounding and the water below the ice layer that is formed. This could be one reason. Yeah.
Indeed. So yes, so ice does act as a layer of insulation, preventing the heat exchange between the water beneath that thin layer of ice and the atmosphere outside. So while the air outside may be much colder, but the water remains warm, quote unquote warm, at 4 degrees Celsius, or maybe even warmer, depending at what depth that we are looking at. And what would you think that leads to? That the water below would never get frozen, and what does that lead to?
It must be protecting the aquatic life within.
Indeed.
And that's, yeah.
Yeah, so that's where when we say water is life, the anomalous behavior of water ensures that the aquatic life, the fishes, the fauna, doesn't freeze to death if the entire lake had to be frozen. But just imagine the consequences if the ice would start sinking, then gradually, if the colder climate remains for long periods, the entire water body would get frozen. And so that's an example how this anomalous behavior is important for sustenance of aquatic life. And we'll keep reiterating these examples to say how water is ice. So Ani, were you able to follow through this few things that we talked about?
Yes, sir.
Which class are you in?
I'm in 6th.
Okay, good. Yeah. All right. Okay, so that was our first experiment with ice and water, and it just tells us how it manifests itself in cases of natural water bodies in the colder climates. Okay. Let's move on to one another activity, continuing to build up from this. Now, Rukmini teacher told us about ice acting as a layer of insulation. Okay, and so we will see that each material does conduct heat. It could be at different rates. So if you are holding a spoon, for example, okay, if I could switch this on. Okay. So if you put a spoon, one part of the spoon on a candle light or on a gas stove which is burning, you would know that in a matter of few seconds, the other end would get very warm or hot, too hot for you to handle. So our next activity is based around the conduction of heat. Okay, are we all ready for it? Yeah. Okay. So I am taking a candle, and then I'll tell you what all materials do I begin with. Balloon. I'm taking a balloon, and I'm taking a balloon blower. And I just have a small bottle through which I'll be introducing water into this balloon. Okay, so let's have a look at this activity. So I'm just using a balloon blower for ease of blowing, while we should also know how to blow it up with our lips as well. So I've just filled in a balloon, and then I'm tying a knot. Many times I see kids not very comfortable being able to put a knot. So you could use a piece of thread to just tie the knot around. And now I am just, okay, let the fan in the room get switched off gradually so that we can switch on this candle. Of course, when we are doing some of these activities would need an adult supervision, which means even the parent takes part in the recreation of this demonstration at home. Okay, so honey, what happens if I bring this filled balloon on top of this flame on the candle?
It may blast.
It may blast. Okay, so be sure that you're not affected by the blast, right? Can I go ahead and blast it?
Sure.
Okay, it may result into a burst sound, so you may want to reduce your speaker volume in case those of you who are wearing the headphones. Okay, let's do that. Yeah, you don't need to close your eyes. I need to. Okay. Okay, so it indeed did blast, right? Wow. Okay, so why did the balloon blast, Suhani? You guessed it right. Yeah.
It blasted because the fire was covering the balloon.
Okay, so yes, so as soon as the balloon came closer to the contact of the fire, it just burst in an instant. What are the other ways that the balloon does blast?
By sharp objects?
By sharp objects. So was this an example of a sharp object?
No.
No, it wasn't, right? So what does sharp object do?
When you just also touch the balloon with a sharp object, it just pops away, bursts.
Okay, right. So it creates a small cavity in the balloon through which the air escapes suddenly, right? And in that escape of air, the balloon also tears up, and so a large amount of air goes out, and that results into a popping sound, right? Now, why does the popping sound happen? It could have just burst without a sound.
I'm not sure, sir, why that happens.
Okay. Anyone wants to take a guess at that, please? So the balloon could have just burst and the air could have escaped. For example, I will just blow up this balloon, another balloon. Okay. And then this time, I can fill it a bit more. And this time, instead of pricking it, I just let the air go off. Okay. And it's similar to the air escaping from the balloon, just in the case, right? There was a sound, but was it bursting? It wasn't, right? So, yeah. So yes, so the balloon, the air escaped, but there was no sound around, right? So these are two different ways that the air escaped. Yeah, Ms. Sugandhi, you want to share something?
Hydrogen.
Hydrogen, you'll have to elaborate it for us.
The air inside the balloon, when it is exposed to heat. Oh my God. Oh, fine.
Okay, no worries. So you also know that the balloon that burst also cracked. Right? It doesn't retain its original shape. You cannot refill this balloon. It just it has just burst open as well. Not just the air that has escaped, but there were large cracks in this balloon. So because of the sudden escape of the air, so air was in pressure when it was being held inside the balloon. You agree to that?
Yes.
While the atmospheric air pressure is much lesser than compared to the air that was inside the balloon. So during this pricking, when the air escaped from a small pocket into large atmosphere, that escape resulted into a burst, which is different from the case when it escapes from the mouth of the balloon. So when it escapes from the mouth of the balloon, it isn't a sudden escape, it's a gradual escape. But since the hole pricks are much smaller and there is a sudden, once the tearing process happens, this being a rubber material, that tearing process happens really fast, thereby resulting into a fast pressure change. And now for a moment, if you can imagine other experiences that we would have had where change in air pressure results into some different kind of hearing. You want to take a moment to think of any other experiences you would have had. It may not be popping, but just different audio experiences of different air pressures. So for those of you who have traveled by a train or by a car and passed through a tunnel, okay, preferably if it's a train with its windows open, if you pass through a tunnel, there's a different audio experience when you are inside a tunnel because the air is contained in a small way. It's not pressurized, but it's contained in a small way in the space within the tunnel. The other example could be just an elevator, okay, where a certain fixed volume of air is logged once you go into an elevator. And then if you really ascend or descend many floors, like 20 floors, 25 floors, you feel some kind of a differential air pressure in your ears. And as soon as you get out from an elevator to an outdoor environment, even if it was peaceful, there is a different air experience on our ears. So we see that the pressure at which, if there's a pressure change, we hear this kind of a popping sound, which was different in the two cases, in case of bursting and in case of air escaping from the mouth. But here we are not so much to talk about the sound and pressure, but to see how does the heat resulted into the thinning of the rubber, okay, which resulted something similar to bursting of this balloon. Right? So when we put the blown up balloon on the flame, the rubber started expanding and started to become thin. And at one point of time, which was very instant, it resulted into a cavity, like a prick in the balloon, and the air started to escape. So let's go on to the associated second example. I blow this balloon again, okay, and this time I have this small machine oil bottle with a small nozzle, and I have filled plain water in this. So I will try to introduce this water in this blown up balloon and repeat the experiment, okay, and see what happens. This is one of the ways I can introduce water in an air-filled balloon. Okay, I hope you can see it. Oops. Okay, now I hope you can see there is some amount of water. I'll try to bring it close. I don't know if the color contrast is big enough, but there's water now at the base of this balloon, and I'll blow it up a little more. Switch off the fan. So I'm using these two equipments, just the balloon blower and so I've kind of, yes, filled air, and if I wish this was of a different color, so you could have seen that there is a small amount of water in this, right? So you'll have to trust me for the moment. Okay, next time I'll have a colored water, like a Neil colored water in this. Okay, so this time now I will again put a knot and repeat the experiment. So this time, Swani, what difference do you expect, if at all?
Teacher, sir, the last time you just blowed the balloon with normal air, but now you're adding the water and re-blowing it.
Yeah. Right. So I'm going to repeat the same experiment of what we did earlier, blowing a candle and putting the balloon on top of it. Are you ready to see? Okay. There's a bit of electronics around, so I would go a little away from this, and I hope you can witness what happens. I'll move this tool. So I've kept a stool and I've kept a bucket, just that in case it bursts, there should be space for water to fall down. And in this hand, I have the candle. Okay? And I'm just putting this. So do you remember how fast the burst was the last time? Yeah, it was super quick. Let's see what happens now. Okay. You see the candle is right below the balloon. Right? And I'm heating the balloon the same way. Sorry, did we do something with the balloon? It's not bursting.
It is not bursting because it already burst that time, and now with the balloon containing water is not bursting.
Yeah, there's something interesting happening, right? It's the same balloon.
But we have filled water in it.
Yes. So what is that water doing so that the balloon doesn't burst? You see, it's a long enough time that I've held it to an extent that even the balloon has become dark with the carbon coming from the candle, right? You see that? It's almost 1 minute of holding this candle below the balloon and it's not even bursting. Okay, we'll leave it at here. Okay. Sorry. Okay, so we saw that we were that we were heating the balloon, which had a little bit of water in it. It also had air. It was not just a water-filled balloon. It was water plus air. There was something interesting that the heat wasn't enough to burst the balloon this time. So, you want to take a guess what happened? Any of you feel free to share?
Sir, can I?
Yeah, please.
I think so that the balloon had a rubber, so it was melting the rubber without popping the balloon.
Can you say that again? It was melting the rubber without?
It was melting the rubber without blasting it.
Right. So
it was boiling inside.
Okay. Okay. Sure. Yeah. So the contact of the flame is indeed with the rubber material in both the cases. When one case on the other side of the rubber was just plain air, and the other case it was water. Right? So one of the natural explanations is that the water is taking away the heat that we are giving to the rubber, and therefore the rubber doesn't expand the same way it would have expanded when it was only air. And therefore the water never spilt out because the balloon never bursted. So it was always cool till the amount of so if you would have continued the exercise for longer duration, and you can see it for yourself, there'll be a point where to a point where, okay, Suhani has shared an explanation. Rubber obviously does not reach a temperature sufficient for it to melt. But why doesn't it reach? We are providing the same amount of heat. The answer is that the water takes away the heat that we are supplying to the rubber to some extent. And there'll be a point where water keeps getting warmer, and there'll be a point where rubber would indeed burst. So see it for yourself. Ensure that you are away from any electronics around. Electronics or any other thing on which spilt water would not be good. Okay, so this was an experiment on conduction of heat, and how water played its role in ensuring that the balloon doesn't burst the second time. Okay. So now we compared these two examples, that if we keep this steel spoon on top of the candle, burning candle, it's a matter of a minute where we would feel the heat from the bowl part of the spoon to the part of the handle part of the spoon, and you'll feel like just dropping the spoon. Right? But that was not the case with the balloon that we burst. So it took quite significant amount of time, because the water could contain some amount of heat before it could let it pass. So each material, metal and water, in this kind of an observation has a different speed at which they conduct the heat from one part of the object to the another part of the object. And this opens up many interesting behaviors. We can talk about them in the due course. So talking of water and heat, does it ring a bell that even in our kitchen, when we cook food, we use different kinds of utensils. When we want to cook different types of meals, or we want to boil milk. So do you see any kind of manipulation of behavior of water, air, etc. That happens on the cooking stove that you have observed? Please feel free to share your observations with all of us.
When we keep the water on the stove, it starts boiling.
Yeah, it does. How much time does it take to boil, say, a liter of water in a small can, 1 liter of milk, for example?
It can take at least 15 minutes.
Okay, yeah, 15 minutes to boil 1 bag of water, milk or water. Okay, yeah. So besides the ordinary utensils, which are open top utensils, we also use pressure cookers. Why do we use pressure cookers for heat, for cooking some, say, khichdi? We want to cook rice, boiled potatoes. We use pressure cooker. Why do we use that? Why don't we use always an open top utensil, just like for boiling milk?
To retain the nutrients.
So are you saying that in the pressure cooker, the nutrients are retained because it's a closed container?
Time is also less.
It saves time, okay.
Sir, it helps in increasing pressure inside, and because of which boiling point decreases and the food cooks, fast. This could be one reason.
Okay, so according to you, the increased pressure, and therefore the name of the equipment is pressure cooker. Increased pressure reduces the
boiling point of the food item that is being cooked. And so food happens to cook fast as compared to the food cooked in the ordinary utensils.
Okay. Any of the other teachers want to add in? Does anyone know the history of pressure cookers, why they were invented? Varsha, you could also answer.
Yeah. I was coming to that. I don't know the history, but I could relate it to autoclaving. I've done my graduation in microbiology. So what we used to do is that we used to sterilize our equipments in an autoclave, which works similar to a pressure cooker. So I don't know exactly where am I going, but yeah, I could relate it to that. So I think maybe if one is, yeah, it saves time, as ma'am said. Also maybe to make it free from organisms. I don't know if that can be also one of the reasons, if I'm relating it to autoclave.
Okay.
While it is boiling, the steam remains inside compared to
Yeah.
that of the open one. Open one, the steam escapes out because of the pressure which is there.
So now, yes, each one of us have observed this phenomenon, and we have our reasons to believe, and therefore we continue to use it. But let's try to put this few observations together, some of which even I would want to add. So what happens if you try to cook food at a high altitude? You would see that it takes the cook gets cooked differently, or it may not cook at all. This is one observation that was done at trying to cook something at high altitudes. As far as the ideas of keeping the steam contained within, or preventing anything from outside getting in, or the nutrients getting out, you will see that the explanation is indeed the contrast. So in case you want to prevent the nutrients to go out, you could just keep a lid, as we do on a milk container, if we do it that way. So when we do cooking at low flame, after a bit of cooking, we put a lid on it and let the food cook in the amount of heat that it has already accumulated, right? And the other thing to notice is that one of you mentioned the food has a particular temperature at which it needs to be, and usually since we have water in most of the things that we cook in, either internal to the material or externally added in, if you're making a gravy, for example. So it's the temperature of water and the water itself that retains that heat and passes it to the ingredients which are in it, be it rice, be it a potato. So water contains that, takes in the heat that we provide through the flame and passes it to the food, because water spreads itself entirely around the food item that we're either boiling or cooking. So you can now imagine that the relation is between the pressure and the behavior of water, which is basically containing the heat and not boiling off. So now we want, for good cooking, the water to be there always. But if the water reaches its boiling point, the water would escape. So how would the food get cooked if it's not surrounded by water? So food cannot get cooked just by contact with the steel pan, right? The food needs to be heated uniformly. Water serves that as one purpose. Also, that just to make it chewable, we need it to be soggy. We need the potato to be a bit soggy, moist. So we have now established that the relation of cooking is to transfer the heat to the water, which envelops the material that we want to cook. And therefore, we are limited by the behavior of water at its boiling point, which is 100 degrees Celsius. Okay. Now, suppose a certain food needs to be cooked for a long period of time. So, for example, certain meat or unpolished rice, for example, demands more amount of time that the heat be passed to it. So, if the water boils off at 100 degrees Celsius, then we will not be able, we get a semi-cooked food item. Now, to retain the water in it, one thing is to just close it by lid, but we cannot let it be closed in a tight bound container, because when it forms steam, it can blast, right? So we need to control the pressure that gets built up inside this container, and that's one reason to use a pressure cooker, which has a whistle setup that allows the steam beyond certain pressure to escape. Now, here is something which resulted into invention of pressure cookers. So at high altitudes, since you would agree that the atmospheric pressure is less, Right? So at low atmospheric pressures, the water would boil off faster than at lower altitudes or at mean sea level. Right? So because the water would escape out faster, you would need to keep introducing more water if that allows some kind of cooking. But most practically, the food would remain uncooked because the water is just escaping and not allowing enough time to heat up the vegetables inside it. So by now using a pressure cooker, we artificially or externally increase the pressure at which the water is inside the container, and thereby allowing the water to come back to its boiling point, which is 100 degrees Celsius, and therefore give enough time to the vegetables that are being cooked. Now, indeed, the pressure cookers were designed to be used at high altitudes, but somehow we have started using them in whichever part of the country that we are in. And one of you really hinted it rightly that it allows faster cooking. And let me now illustrate why does this happen. So when we use the pressure cooker at low altitudes, we are further increasing the temperature at which the water boils. So water may boil at 101, 105, even 110 degrees Celsius inside the pressure cooker because it's contained in a pressurized environment. Now, what happens with that is that the water is now absorbing the heat, not changing into steam, but then allowing the food to get cooked faster at higher temperatures. So it's possible now to have more than 100 degrees Celsius even within the container, and thereby the physical and the chemical changes that happen in the item being cooked happens at a much faster rate. So any transformation that's happening in the texture and of the material would accelerate at higher temperatures. So this pressurized environment allows higher temperature inside the container, and therefore we get food much faster compared to an open top container. So I hope you got this connection of why were pressure cookers invented to be able to cook food at higher altitude. And if we use the same concept at lower altitudes or it's around sea level, which is what Mumbai is at around, we are able to cook the food fast. I would just leave you with a comment. If you read closely about the nutritional value of certain foods, it's good if we do not superheat a food item, then it indeed loses its nutrition or it could turn toxic in some cases. And therefore, cooking food at low flame, but cooking it for a longer duration retains its nutritional value, and hence it's recommended in many school classes, but in many schools of thought on cooking and culinary as compared to using pressure cooker for cooking. Yeah, good. It's about an hour. We could take a couple of minutes break if you want to just move around a bit, and we could reoccupy our chair for next 30 minutes. We have this session until 5:30. I have a few more experiments to talk about. We'll take a 2-minute break and come back to our position. Yeah. Varsha, is that okay?
Yeah, okay, sir. Yeah.
Slow pace.
Yes, physics teacher.
Yeah. Welcome back all. Can we start? Can we resume? If,
Yeah. Yeah.
Yeah.
Yeah.
Ms. Rukmini, Ms. Sugandhi, are you back as well?
Yes, sir. Yes, very much.
Thanks. Yes. Okay. So this was a glass. Okay. So this is a glass in which the ice has become water by this time. Okay. So I have a few things about on the properties of water. These are something that we see every day. So I have salt, I have sugar, and I have a bottle of mustard oil. Okay. So Suhani, okay, since you are the only student in the in the group, I am my questions are to you. Yeah.
So one more student, Pavana Priya will be this, sir. One more will be
Yeah.
there.
Yeah. There's.
Okay, so we have more students that have joined by now, which is nice to know. Okay. So can we see Pavana Priya as well? If you can switch on your video for a minute, introduce yourself a bit. Hi, Pavana Priya, can you unmute yourself and say hello to all of us in this session? Okay, never mind. We'll continue. So I have sugar, salt, and so let me reorient my video view. Yeah, okay. So Swani, if I take this salt, some amount of salt, and put it in this filled water filled glass, what would happen?
Dissolve.
It will dissolve. Okay. So I've indeed put certain amount of salt. I can put even some more. Yeah. Will it keep dissolving if I keep adding it more and more amounts of salt?
No, sir. If we stir it, it will start dissolving.
Okay. So you see earlier the coin was very clearly visible earlier before I put the salt, and there's some amount of salt I can see still at the bottom. So let's do the stirring as you said. Okay. So the visibility of the coin is an indicator whether the salt is completely dissolved. So you still see this, there's some amount of salt right on top of the coin. Right? So it's not fully in. So let me stir it continuously. Okay. I've stirred it. Do you see the coin is better visible now compared to earlier when there was some amount of salt in it? So indeed, what you suggested happened. Okay? The salt dissolved, and so now one question: can I separate salt from this water? Like I can lift this coin and I get back the coin that I had really put in. Right? I get the coin, the 5 rupee coin. It's safe. I can buy something with this 5 rupee coin. Right? But can I recover the salt from this water?
No, sir, because you have already added the salt and dissolved it with the water. We cannot separate that.
Okay. So if that is true, then where do you think this salt came to my kitchen? Where did I get this salt from?
From the sea.
From the sea. And is salt dissolved in the sea, or it's there in some cave inside the sea?
It is completely dissolved in the sea, as the ocean seas are salt water contains.
That's true. So what is there in this glass of water is a representative of salty water which is out there in the seas and oceans. Right?
Yes.
Okay. So here, according to you, we cannot extract the salt from water, but then this salt comes from the salt that's dissolved in seas and oceans. How does this happen?
There is a process in that, but we have to do the process using the salt water to get back our salt.
Okay, so now you say that there is a possibility through which we can extract salt from a salty water. Do you know how does this process look like, or what is it called? Never mind. Okay. So teachers, this is interesting that we can replicate what happens on the beaches. So if we go on a salt pan beach of Kutch in Gujarat, for example, one of the places on the coastal belt of the country where large scale salt extraction from the sea does happen, we see those salt pans just beside just beside the seas. Okay. And so we are able to kind of replicate in a small environment what happens at a large scale out on this planet. So this is one way I would think we can reach out to these students in our classroom to kind of scale down a natural phenomena onto something which is a tabletop phenomenon. Okay. So Swani, we will come back to the point of knowing more about the process through which. So what happens if I just keep heating this salty water? Keep heating that the water becomes very, very hot. What would happen to the water?
It warms, it starts boiling.
It starts boiling. So if I keep boiling it for say 15-20 minutes, what would happen to this glass of water? What would happen to the water in it?
It keeps boiling and the salt extracts.
Okay, so the water would boil out completely, and I may not have water at all, but what would remain is salt at the bottom of this glass. So that's one way. So if I have salty water, if I keep heating it, boil the water off, what remains in the container would indeed be salt. And this is what exactly happens in the salt pans, which are located near the coastal parts of our country or any other country for that matter. And same could happen with this crystals of sugar, but I would want you to try this experiment at your home. Okay, moving on, in the interest of time. Shani, what cooking oil do you use in your kitchen? Do you know that?
Yes, sir.
Which cooking oil do you use at your home?
Sunflower oil.
Sunflower oil. Okay, okay. Do you do cooking sometimes? Do you help in cooking?
Yes, sir.
Okay, very good. Okay. So let me open this bottle. Okay. Okay. So Swani, I am going to put some amount of oil, okay, in this glass of water. Where do you think the oil would go?
It would stand in the bottom because you're adding it in the salt water. It may flow. Sir, can you hear me?
Yeah, we can hear you. Can you say that again for all of us to hear you clearly one more time?
So you're putting the oil into the salt water.
Mm-hmm.
It may stand up, float.
It'll float. Okay. Okay. So it would not sink. Okay, let's do that. It would have been nice to see this through. Let me try to put the glass on the front camera and see this. Okay. Let me wipe off the condensation. Okay. And make it more clear. Okay. So I am continuing to introduce oil in this. Okay. So Ani, how did you guess it so rightly?
Sir, because I've tried this experiment in my home.
Okay. Which oil did you put in water?
The oil, sunflower oil, which my mom cooks with.
Okay, okay, indeed. That's interesting. So now what if I try to mix this oil and water? Just like I mixed salt and water?
So if you try mixing, it also stays about.
Okay, that's very interesting. So let's give it a try. Here is oil, mixing. Yeah. The yellow color is spread out now, right? It's not just at the top, but let me leave it for a moment. And then the oil is back again at the top. Very, very interesting phenomena. So as you see, water behaves differently for salt and differently for oil. And that opens up, to me, it opens up a lot of questions of what if metals, would Earth be the same way if many more things got dissolved in water? It may not be. Right? If minerals, all minerals, all sand would get dissolved in water, we may not have the planet on which there's dry land. Right? So this, it will be interesting to see how different materials behave when they interact with water. Okay. So continuing one more short activity after this. If anyone has questions around this, you can try with a few other materials. We had a piece of candle a while ago. Right? So, sorry, you know if what happens if you put a piece of paper in a glass of water which is filled? What happens to the paper?
The paper gets wet and it automatically it gets wet and it starts coming out if you put a tissue paper.
Yeah, so
wet.
So the paper soaks the water and it weakens up. What happens if I put this candle in water like this? And then if I remove this, does the candle have the same fate as the paper?
No, sir. It is perfect. The candle is normal. It is not wet. A lot of wet. It is not completely soaked.
Okay, right. So give it a try and let me know which. This is a small assignment, homework assignment for you. Let me know that the materials that you find around your home, easy to access materials, which one of those soak water and which ones remain perfectly as they are and do not soak it at all. Yeah. Can you note that down as a small homework assignment and share it with all of us later?
Sure, sir.
Thanks. Okay. So that's with the interesting properties of water. And now let's look at some more. I need a bowl. Okay. Now, in theme of water is life, let's relook at the trees around us, the vegetation around us. So we would all agree, we would have witnessed this, that even if you grow a small plant at your home in a pot full of soil, you do the watering of the pot right where the soil is. Right? But then the leaves, the branches, the fruits all come up in the air and they're green. And we know for leaves to be green, they need water and they need few other natural elements. So, Sonia, are you saying something? You are muted.
No, sir.
Okay. So the water that we put in the pot, okay, reaches to the leaves and the branches, right? Now, how does the water go from down below, from the soil to the leaves, which are high up, which is like something like anti-gravity. Usually water would fall from top level to lower level, from a higher level to a lower level. In case of trees and plants, the water goes from lower level to higher level. So how does that happen? Have you really wondered this ever? Anyone could answer this?
The roots absorb and the water goes through the xylem vessels to all the parts.
Okay.
The process of osmosis also plays a very important role over here.
Mm-hmm. So there are certain vessels through which it goes up. There is osmosis.
And due to transpiration over evaporation of water, the pressure increases. It pulls up the water. Upward force.
So yeah, sorry, please.
Due to transpiration, the water losses, it occupies that water pressure, it is sucks up the water from the root.
So-
Ascent of sap. Yeah.
Yeah, sounds good. So we have at least 3 explanations, all of which play an important role: the vessels in the tree, the osmosis, and the transpiration, which results into the water going from the soil to the leaves. Now, if we have a very young student like Suhani, how do we demonstrate this in a simpler way, without necessarily oversimplifying? Because we are yet to get introduced to the plant biology to be able to understand this, or some more, I would not really say them higher level scientific concepts, but something that we eventually learn to someone like a 6th grader like Suhan. So I have a small demonstration, and let's see how it helps us see what's happening in some way, what happens inside the tree. So Suhani, do you feel curious enough to know how water goes up?
Yes, sir.
Okay, let's have a look. Okay. So I've taken, okay, let me clean up the space a bit so that you know what all materials we are using. Okay. So I have this bowl. Okay. Intentionally, I'm keeping it transparent. And I have this meal powder that we use for in washing of our clothes, especially the white colored clothes, also called as indigo. So what I would do is to put some meal, or maybe before I do that, I want to show something related. Okay. So I'm just putting some amount of water, okay, in this bowl first. Okay. And I have a shoe string. I know my video has frozen, but okay. So I've taken some amount of water in this, and I've taken elastic waist cord that we put in our elastic pants. Okay, or you could also take a shoelace, which is white in color. Now, 1/2 of it I put in. So what would happen if I just put this shoelace inside this water, inside this cup? Sonny, you'll have to unmute.
It soaks.
It soaks in water. But what if I put in just 1/2 of it in the water? What happens?
The half soaks and the half is dried, which you're keeping in the hand.
Which I keep in here, right? So this is what exactly I have, right? Do other teachers sense something in this? Is something interesting going to take place? So you can do this, Suhani, and experiment at your place later. But just to highlight this, I'm putting some amount of meal in it, right? And let me mix this meal in this water. So now I have blue water, dark blue water, okay? And so you see that if I lift this, the one part of the, so if I keep it here, the one part of the shoelace that has soaked is blue while the other is white, right? So I'll put this in again, okay, and wait for a while. You know. And I'm not going to do anything. Let me, for better visibility, let me yeah, just readjust this. So this is the arrangement. So Sonny, what I'm observing, and some of the teachers would have known the outcome of this, is if I hold my hand on the dry part, I would, in a matter of few minutes, would see that even the dry zone, which I expected to remain dry because it's not in contact with the water, starts to soak. And that to me came as a surprise. I hope a bit of this experiment can can highlight that there's indeed that water, which is the water is flowing through this, though I did not expect it to flow. Right? And that in a way kind of resembles how one would imagine that the water flows up from the roots to the leaves of a tree. So for those of you who would have tried this, you can feel it for yourself again. And even the homemade lamps that we make are a good way to demonstrate how the oil continuously sustains a flame in the cotton wick that we use to keep that lamp alive. Otherwise, the cotton could have easily burnt. But there's something that is continuously fueling that small piece of wick to be continuously burning. What I'm definitely seeing, but it may not be very prominent in the camera, is that the blue color is gradually rising up from the water level. Right? This is more closely observable. It may take quite some amount of time depending on the nature of the rope, but definitely the entire good amount of rope is now moist. So we are pretty much at the fag end of the time limit set, but before I think there is an option to show some more, I would want to invite questions through any of you participants from what we started this session today to what we have shared so far. I want to open the floor for any questions on what we have talked or anything that has occurred to you during this conversation. I hope many of these items I was able to source around from kitchen or a local utility store. So there's no very special purpose material that I have arranged so far in the demonstrations that we have seen. So I hope they are replicable at your end. There are a few more experiments and I would want to share those with you. I'm sure there are video resources for those. So since we have your contact numbers and email IDs, post this session, we'll share with you a compilation of experiments around water as a theme and experiments on other concepts of science, which can be readily done through you in your home environment. But a setup like this, where you have a single web camera and also a phone, can enable you to demonstrate something on a tabletop kind of environment as well. So they fulfill some of the expectations. I'm guessing that 1 hour 30 minutes is insufficient for so much to explore all the properties of water that we know of, or some that we may observe but we may not fully realize why does this happen. I would love to hear some comments from the participants today. Varsha, you could set the ball rolling on the comments side.
I just remembered one thing when you were talking about the pressure that we experience in elevators. Is the same kind of pressure? Is it the same kind of pressure that we experience if we are going through some water sports or some water sport like scuba diving or something like that? Because at that time the pressure is quite immense. Especially I remember when we went for scuba diving, I could feel the pressure in my ear, and also I had a cavity, so I could also feel it there. So yeah, is it the same thing that we might otherwise feel on higher altitudes?
Yeah, the short answer is yes. There's a pressure variation all across the altitudes of the earth, right from the top of the Everest, and therefore people wear oxygen cylinders there because there isn't enough pressure to breathe. And also at the depths of the sea, where we go for scuba diving, because the density of the water is more than the density of air, and that exerts extra pressure on the inner eardrums as well. And we need to continuously equalize, which is try to create a pressure from within the body on the ears so that it's balanced, and then the inner ears don't get injured or ruptured during that sport. So the way we do it is close our nose and try to blow out air, and you will see that. You want to try that. This also happens in airplanes. If you feel that your ears are paining, one of the way to restore or equalize the balance on the inner ear is to close your nose and try to blow out air. So close your nose and close your mouth, try to blow out air, and you will see that the air is trying to escape from the ear cavities and therefore balancing the inner ears.
Great. Thank you for the tips.
Yeah. That's something we get trained when we do scuba diving under certified instructor.
Okay.
And I have a few slides to show just to add up to it. I certainly felt we could do more of a conversation, which is what we have done. But let me try to share a screen quickly. And
I think Suhani has some question.
Please. Yeah.
So, just now, as ma'am said, can this also be an experience when you complete your smoothie and there's little, when you observe the, like, when you use a straw to drink it, you get some sound when there is a leftover in the smoothie.
Okay. So let's relook at that phenomena, what you just shared. So if you have a coconut water, a coconut having water, or a soft drink that you are drinking, initially your straw is fully submerged. So what you are sucking in is the drink that you are relishing. But when that comes to an end, then what you're sucking in is a combination of air and that liquid, the coconut water, for example. And so you suddenly start to hear a whistling sound in that. So that is related to, so the straw acts as a resonating column, which is what a flute is. So if you have a flute and you try to blow a flute and try to keep different holes opened or closed, you hear different frequencies, different sounds. Okay? So the straw acts as a resonating column, and it behaves differently when there is liquid, when there is no sound, and then when there is a variable amount of air. So so the sound gets changes when you are trying to suck in the last drop from the coconut, piece of coconut. Yeah. So that has to do with the air and the size of the straw, and length of the straw as well. Okay, so I'm sharing my screen, and since Varsha talked about scuba diving, one of the related sports that I engage in is kayaking. So this is me sitting behind a young student, a 5th grader, and we are doing kayaking in a water body near Mumbai. Is this visible to all? I'm hoping. Varsha,
yes.
Yeah. Okay. Okay. So very quickly, I would want to run you through these. We have done some of the activities, but these are other ways that I connect to water, and I hope many of us in this session also do. Right? I want to do a survey, and let me switch to the gallery view. How many of you are comfortable being in the waters? If you could do a raise of hands, or just type in the chat box about your comfort being in the water or your fears of being in the water. Swimming is one classic example where it gets highlighted. Swani, have you learned to swim?
Yes, sir.
Okay, Varsha also gives a thumbs up, so she's comfortable. I want to invite response from other teachers in the group. You want to express it, you'll have to unmute. It's okay that if you have extreme fear of being in a swimming pool, that's totally okay. But it's good to know. Yeah.
I I don't know swimming, but okay, I feel comfortable in water.
Right.
Yes, yes, same. Don't know swimming.
Okay, that's quite good.
Calling, yeah.
Yeah, sure. Since we are officially out of the scheduled time zone, I just want to take another 5 minutes, but feel free if you have other commitments to cater to. But this is one interesting way to be comfortable with water. There's a whole life. There's a whole different experience once you get comfortable swimming in the waters. Okay. Typically, we understand that relations is with human beings, and we occasionally talk about relationship with nature. But as you know, the properties of water and other materials engaging with water is very intriguing. And to me, that is also a very valuable relation. We did not talk about the role of water so much in our lives. We talk more on the science of water. But I have discovered a lot of this in the recent years, and I hope our conversation like this will continue in the coming sessions as well, where we explore about how do we get water at our place. It's nice if the fear of water goes out at early ages, and that that in a way helps build strong relations with being inside water. So activities like scuba diving, snorkeling, or kayaking, which do happen in and around Mumbai, Thane, wherever we may be living, helps us expose. So if you're planning a school trip sometime, it could be around a water body with necessary safety taken around, be it Powai Lake or Upwan Lake in Thane. Many of us do witness the diversity of aquatic life through television programs on Discovery and Animal Planet, but it's possible to witness them firsthand if we also get to know a little bit about the aquatic life in our immediate surroundings. While we may have...
I think most, like all of our teachers are from Bangalore.
Okay.
So...
Oh, I'm sorry. I had a wrong assumption. Okay, so Bangalore indeed has many more lakes. There's, and I know many of them are in poor shape. I used to stay near Belandur Lake on the old airport road. I used to also pass by Alsur Lake. These are two prominent lakes besides many others. I think Maratharli has another water body around it. So just like the water bodies around Mumbai are facing the challenge of not being in good condition, so is the case with lakes around Bangalore, which have froth at times or water hyacinth at other times. But nonetheless, acquainting ourselves with the small or big water bodies is a good excursion, as and when it allows you to schedule a school trip. So while we are familiar with water coming in our home through taps in the wash basins and the sinks or through the tanks, but it's also useful to know how a lot of other underdeveloped places, or rather natural places, had access to water. So generations before used to access water from wells, carry it on their head before we got the plumbing infrastructure, the long distance pipelines that could connect all of us living in the urban areas with the water bodies. Okay. This is next. This reminds me of the childhood times when we would siphon the water from it.
Sir, we couldn't see your screen. Are teachers able to see the screen? No, sir.
Okay.
Yeah.
I'm sorry, I had paused.
Yeah.
Let me resume. Okay, I will share what I missed out. So, okay, I was on swimming as a screen, and then I mentioned that typically we understand relationship between human beings, but as we discovered, water is very intriguing. It is pertinent that we build relationship with water as well. We talked a bit about water sports, but it's good if at a young age we expose ourselves to water sports, that the fear of water goes away. I was mentioning that the aquatic life that we experience on television could also be experienced in live. There are enough opportunities. And I then switched the idea to the fact that not few decades ago, the plumbing infrastructure that we have seen around us, enabling us to live comfortably in urban dwellings in high-rise buildings, wasn't the case. We would manually take in water from the wells carried around before the long-distance pipelines enabled us. Like, for example, the water in Mumbai travels 100 kilometers from 3 big reservoirs. Marsha would recognize these names: Vaitarana, Tansa, and Bhatsa, the 3 major reservoirs, but they are located very, very far away from the Mumbai. And every day, millions of liters of water gets transported at a significant energy cost to be made accessible to the people. Right? So, for those of you who would remember their childhood around bore wells of this nature, where we would siphon out the water through this kind of a hand pump. Many of us, the younger generation is unfamiliar of the fun around water through this kind of interaction. And similarly, the technology in our homes has replaced the traditional ways we would engage with water, and washing of clothes is one such example. So for most of us, these are the two, the sinks and the wash basins, and some of these tanks are our only means to know how water reaches our home. But there's a lot more that we can talk about, either through video screenings or through excursions outside, to know how does the water gets in from the lakes, from the rivers, gets filtered at the water supply board before it reaches the high-rise tanks in the city, and then it reaches eventually our home. So Google Maps tells us how to reach from place A to B, but there aren't such prominent water maps which tells us how does water reach our homes from the water bodies. So this is one segment, and just one of you did mention about the poor state of water bodies around us. So I also participate in projects which involve restoration of water bodies. This is one example of a river near Mumbai, which was extensively covered. About 20 kilometers of length of the river was covered with water hyacinth, and through an appropriate intervention, we were able to restore the river body. So COVID has told us how air could be a media that the disease could transmit, but imagine if the diseases of this nature get transmitted through the water bodies, which may already be happening, because we put in so much sewage and toxic waste in the water bodies. How do we cater to the requirements of lakhs and crores of people which reside in urban dwellings? So this is just a very short glimpse of what I have explored about rivers, about water. Once I was out of the school and the textbooks, many of these learnings have come through personal exploration. So I hope with this session, I was able to excite you a bit to rediscover and rebuild the relationship with water. And yeah, I would want to take a pause there and host any questions from any of you. Thanks for being a patientful participant during these 2 hours of interaction.
Oh, thank you, sir, for a nice explanation. And again, we are able to recollect all this. We will try to reach out to our kids, our students, the earlier method, how they are able to take the water, the source of water, everything. We'll just make them to understand. A nice experiment, easy. What are the experiment you have shown? No, that is easy, and we can use it in our class and then do it. Thank you, sir. Thank you for your valuable time.
Yeah, I think anyone else, any other teacher wants to share the experience? Yeah, Swani wants to show something.
Yes, sir. Sir, you asked me to write something before which soaks and which doesn't soak.
Yeah, good. You're super quick at that. Please tell us.
Yes, sir. The soaking materials are napkins, sponge, paper, towel, face cloth, chalk, and cotton balls. Whereas the non-soaking materials are styrofoam, Ziploc bag, wax paper, aluminium foil, marker.
Ah.
That's very good.
This was super quick. I would want to leave you with one more quick demonstration. This glass in the white cap. This glass. Okay.
Just shine.
So just a very quick demonstration. I think I should be able to show it standing up, and we'll conclude on that. So I have this transparent glass and a lid of a plastic jar, right? So if I just keep this lid and then reverse it, you would know that the lid just falls, right? Okay, but let me also switch on this camera and see you get a better view. Okay. All right. So it's okay if things scattered around a bit. Yeah. So here is a glass with a lid. Okay. If I just reverse this, the gravity would just pull this off. Now, what if I just put some amount of water in this? Okay. And then repeat the experiment. So I've kept the lid on the top and then reverse the glass. Okay. You can see this. And okay. Wait. It would have still fallen. I observed something interesting today. I just need green one. Okay. So let me try it with a different lid this time. So there's some amount of water filled in this, and there is a lid like the one before. And then I just reverse this, and bingo. Do you see this lid not falling off? Yeah. So, Ani, was it something magical? Could you see it? Yeah. So this is a lid with just a lid of a small plastic container. I keep it on top of a glass, covering its mouth, reversing it, okay, and just pressing it a bit, and then leaving it. Yeah. So there's definitely some amount of science behind what appears to be magic. And I think one of the science fiction writer has said, I think Arthur C. Clarke said, Varsha, if you can help me on that, something that's scientifically so advanced is indistinguishable from magic. So sometimes science manifests in front of us in certain ways that feels like almost unimaginable. This was just a short glimpse of that.
Yes.
Yeah. So, yeah, we should all welcome each other to the magical world of science, especially around water, yeah, and unravel what's behind those magic tricks or magical observations. Yeah. Thanks. It was such a nice evening interacting on many of these facets of water.
Yes, thank you so much, sir. And I would, especially mention here all the teachers who have, and Suhani also, and we also have a student with us, Pavan Priya. So I hope that Sugandhi ma'am, if more of your students are interested, you can surely contact us, and I hope that we have this session the next time with all all these curious minds like Suhani. So definitely I think we'll keep in touch, and you can always I'll share the details. You can always write to us and also contact us. we'll also forward any of your requests, or if you want more such experiments or more such sessions, you can always request for those, and we'll be in contact with Deepak sir. Also, if you try out some experiments at home, you can definitely share it with us, share it with Deepak sir too. Yeah. So thank you all of you. I think today's evening was just a great experience. Thank you so much, Deepak sir. Thank you so much, all the participants. And we'll be sharing you a link of feedback form. You please share a feedback with us. Thank you so much. Thank you so much, Suhani. Thank you.
Thank you, one and all. Yeah, and feel free to reach out. It will be nice to discover something together in this process. Yeah.
Thank you. Bye.
Thank you, sir.
Thank you so
Thank
much,
you.
sir.
All right, Sohani, thanks for this. Your participation was very much appreciated in our today's session. So we had a good balance of teachers, parents, and educators in this. It was good. Thanks for making this happen.
Thank you.